In this video, we'll discuss the question paper 5-2 of the 9701 chemistry, that is A levels chemistry of the examination series May-June 2024. We have already discussed question 1 in our earlier video, and in this video, we'll discuss the question 2. Along with discussing the question paper, we'll also be discussing some important tips to solve the paper 5, that is which applies in all the paper 5, that is in general we'll discuss the examination tips to solve paper 5. So here is question 2, which says this question is about an experiment to investigate the effect of temperature on the equilibrium constant K1 for the reaction shown here. And here is the reaction where we can see that ferric ions are reacted with the sulfur cyanide ion and SCN minus ions, and another ion is formed, and it says that data collected is used to determine the value of the enthalpy change of the reaction. The setup of the equilibrium: aqueous iron 3 nitrate is mixed with the aqueous potassium thiocyanate, and the aqueous iron thiocyanate ions have a red color. A colorimeter is used to measure the absorbance of the reaction mixture. A calibration graph can then be used to determine the concentration of the FeSCN, that is iron thiocyanate ions, in the reaction mixture. And here is a table 2.1 shows the solutions for the experiments, where solution A has the ion of thiocyanide with the concentration given here, B also given here, C and D also given here with the different concentration we can see. And let's go ahead with the first A part, where it says describe how you would prepare 100 centimeter cube of solution B from solution A. So here is solution B, which we are going to prepare from solution A. That is, we are going to decrease the concentration of 0.00920 to the concentration 0.0020 concentration, and include a calculation of the volume of solution A required for the preparation of solution B. Give the name and the capacity of any key apparatus that should be used, and write your answer as a series of numbered steps here. So if we find out, okay, here are the concentration required. So here I'll show you a simplest method of calculation which I generally teach my students, which they find it very easy, is that if we have the concentration of 0.0920 and if we are going to dilute it to 0.0020, and if we are going to prepare the solution of 100 centimeter cube, then what is the concentration of this, what volume of this concentration solution is needed? So this is how I find out, and I always tell them to cross multiply. So it's 0.0020 multiplied by 100. So let's find out that volume, showing the calculation here. It is that 0.0020 multiplied by 100 centimeter cube divided by 0.0092, and this is how we get the volume of the volume of 0.00920 concentration solution required to prepare 100 centimeter cube of solution to dilute it up to the 0.0020. Okay, and we get the answer as 21.75 centimeter cube. So this is how we calculated the volume which we require to prepare our solution. Okay, now we need to describe it in full. It says include a calculation. Okay, that's done. Give the name and the capacity of any key apparatus that should be used. Okay, we'll do that, and write your answer as a series of numbered steps. So first step what I'll write is that transfer 21.75 centimeter cube of 0.00920 moles per dm cube of thiocyanate ion solution with the help of burette, into 100 centimeter cube of volumetric flask. Now we know that volumetric flask is the apparatus which should be used to prepare any of the standard solution, and volumetric flask comes of different capacities. So here we have used 100 centimeter cube of volumetric flask, we have got 250, we have got 500 centimeter cube also, but as we are supposed to prepare 100 centimeter cube, so we are taking the capacity of 100 centimeter cube volumetric flask. Now the second step is that dilute the solution up to the mark in volumetric flask with distilled water. Now we need to be very specific, so here we should mention that with the help of distilled water, and shake well. So both the steps should be very clearly written with all the specific volume capacity of the apparatus. So we need to specify burette is used, we have also specified the concentration used, and we also specify that the distilled water is used to dilute the solution, and at the end shake well also, because that carries marks. It's clearly written. Write your answer as a series of number steps, and the key apparatus should be specified. So all of it is specified here. Fine, let's go ahead with the next part, where it says before starting the experiment, solution B and D are used to produce a calibration graph. Known volume of each solution are added together, and the absorbance for each mixture is recorded. The calibration graph is shown in figure 2.1. The concentration of solution D is much greater than the concentration of solution B, in order that the solution D is in excess. Suggest a reason why solution D is in excess. Now if we are adding any of the solution in excess and we are producing a calibration graph, that clearly shows that we want the other reactant of the solution to react fully. So we can mention here that solution B reacts fully or completely also we can write, and concentration of FeSCN, that is ferric cyanide solution, is known. That is the reason we add excess of D solution. Here is the calibration graph of relative absorbance up to the concentration of ferric cyanide solution per mole per dm cube. The next part is the following experimental procedure is used. Half fill a large beaker with water at room temperature. Transfer about 40 centimeter cube of solution B into a boiling tube and place the boiling tube in the beaker of the water. So we are adding the solution carrying a boiling tube carrying the solution B into the beaker carrying the water at room temperature. Transfer 5 centimeter cube of solution C in a test tube and place the test tube in the beaker. Now before we go ahead with the procedure, let's understand what is solution B and what is solution C and D. Here it's written that the solution A and B are thiocyanate solution, and solution C and D are the ferric solution, that is ferric nitrite, what we have used here, ferric nitrite, and potassium thiocyanate is the solution which are used. Here let's go ahead and understand what is happening. Wait for 10 minutes, that is the step 4. So what are we doing? We are reacting solution B and solution C and waiting for 10 minutes. Transfer 5 centimeter cube of solution B from the boiling tube to the test tube containing solution C. Again stir the mixture in the test tube and record the temperature of the mixture. Measure the absorbance of the mixture in the test tube using colorimeter. So understand what is happening. First, we are taking solution B in one of the boiling tube, allowing it to stand in a beaker so that we get a constant temperature of room temperature. We are taking solution C in a different test tube, and again that also is kept into the beaker with water to again make the temperature of the solution constant at the room temperature. We are waiting for 10 minutes so that the temperature of both the solution remains constant at 25 degrees Celsius, and then we are mixing the solution B and C. That's how we are doing, and obviously the red color will be produced, as we have seen that the ferric cyanate solution is red in color. So measure the absorbance of the color with the help of colorimeter. Now change the temperature of the water in the beaker. Repeat step 3 to 6 for different temperatures. So 3 to 6 is that we have the same boiling tube, solution B 40 centimeter cube, but only step 3 onwards we will change. We'll repeat at different temperature. So identify the dependent variable. Now understand what is dependent variable, independent variable and controlled variables. Now I will say that independent variable is what we change, what the factor which we change. The factor which we are changing is the temperature, right? Can we see that? Change the temperature of the water and repeat. So we will repeat the experiment different temperatures. So independent variable is the temperature. Dependent variable. Now dependent variable is what we measure. So what are we measuring? We are measuring the absorbance of the color, absorbance of the light. So dependent variable is the absorbance. And what are the controlled variables? Controlled variables are the factors which are kept constant throughout the experiments, different experiments. So what are the controlled variables in this experiment? So we'll say that the concentration and the volume of the solutions what we are mixing, that we are keeping constant throughout all the experiments. So that are controlled variables here. So what is an independent variable in our case? That's an absorbance. Absorbance is absorbance of the light. That is the dependent variable because that is what we are measuring. Okay, next part is the describe how you would adjust the temperature of the water in the large beaker to obtain the temperature of 10 degrees Celsius. Now understand what is happening is that the temperature was kept constant at 25 degrees Celsius of room temperature, and we have taken the water in the beaker to maintain the temperature. Now if you want to decrease the temperature to 10 degrees Celsius, obviously we need to decrease the temperature with the help of ice. So we can say that add ice to the beaker till the temperature reaches 10 degrees Celsius, which I am not completing the sentence, but you can write. The main part is that add ice to the beaker. Okay. A student obtains results given in table 2.2, and here is the table where the temperature is 25, 55, relative absorbance is given, and the concentration of FeSC and 10 minus moles per dm cube and K1 is the blank constant here. Now okay, the value of equilibrium constant K1 can be determined using the equation 1, and equation 1 is given here. X is the value of the concentration of ferric cyanide solution in moles per dm cube. Use the calibration graph in figure 2.1 to complete the column 3 in table 2.2. Record the values to 1 decimal place. Okay, column 3 is the ferric cyanide solution, and the temperature is 25 and 55, and relative absorbance we have to see, and they have told us to use the calibration graph at figure 2.1. So here is figure 2.1, and okay, the relative absorbance is 0.60. Here is 0.60. We can draw a line. Obviously I'm not drawing the line with the scale because I'm drawing it on the screen, but you can use a scale to find out the exact line to draw and find out the concentration of ferric cyanide solution with the help of the graph. Now you can see that here is a 9, but I have got the line between the two major lines, so it should be 8.9 because it's not exactly 9 and it's not exactly 8.8, it's 8.9. So one of it is 8.9, so let's add 8.9 into 10 power minus 5 moles per dm cube. Next is 0.42. 0.42. okay, here is again the graph. So 0.42 is here. Let's complete the graph by extending the lines here. 0.2 here, and let's find out what is the concentration of ferric cyanide solution, and we can see that it's exactly 6.2 because the one square corresponds to 0.2 into 10 power minus 5 concentration, so it was 6.2 into 10 power minus 5 moles per dm cube. And now we have to find out the value of K, but let's go ahead and read the question. It says use equation 1 to complete column 4 in table 2.2. Record the values to the nearest whole number. Okay, we have to find out the whole number. Now here is the equation 1 given. It says X is the concentration of ferric cyanide, so we can substitute 8.9 upon 0.0010 minus 8.9 into to the power of square, and that's how we find out K value. Fine, let's calculate it. Okay, I forgot to add here 10 power minus 5, here also into 10 power minus 5. That's how we calculate. Okay, and then let's calculate K1 value. So we have 107 and 70. That was the value, and as we are told to write the value to the nearest whole number, and that's how we have written 107 and 70. Let's see what's the next part of the question. Here says another student does the same experiment for 7 different temperatures, plot a graph and draws the line of best fit as shown in figure 2.2. and let's have a look at the graph. It says 1 upon temperature, that is per Kelvin, is x-axis, and log of K1 is on the y-axis, and this is how we have got the graph, a grid with a straight inclined line drawn for the best fit line. The theory predicts that the relationship between K1 and T is given by equation 2. Here is the equation 2. Delta H is the enthalpy change of the reaction and T is the temperature in Kelvin. It's given here. Explain why the graph supports the relationship between K1 and T given in the equation 2. Okay, let's have a look. So what is plotted on y-axis, that's log K1, and what is plotted on x-axis is 1 upon T. Here we can see this is 1 upon T, and it equates both the equation with some constant here. So if we look at the graph, we can say that the substance on the value which we have taken on y is directly proportional with the constant and T. 1 upon say x-axis. Actually x-axis directly what we have taken, so it's directly proportional because with it is equated with an equal to sign. So yes, we can say that the graph supports the relationship between K1 and T, as we have got a straight inclined line. Yeah, so we have got a straight line graph is obtained, straight line graph is obtained, and that's why the equation, the graph supports the equation. Okay, circle the point on the graph in figure 2.2 that you consider to be most anomalous, and there were no errors in the measurement in the experiment. A student correctly suggests that the anomaly was caused because the absorbance was lower than expected by the line of the best fit. Suggest why the absorbance was lower than the expected. Okay, let's have a look at the anomaly here. Anomaly here is this. And yes, if we can say that the equilibrium K1 value is here it's lower, that's why the log K1 value is also lower, and its reason given is that suggests why the absorbance was lower than expected. Now if absorbance is lower, that shows that the color produced was less. If the color produced was less, that shows that enough volume of the solutions were not added. Here they have clearly shown that the measurements were done correctly. There was no error in the measurements. So what can be wrong is that if the color is low, the volumes added should be low. So we can say that all the volume of solution B is not transferred or added to the mixture. That's what we can say, because then the volume of the solution will go low and the absorbance will also be low. Okay, determine the gradient of the line of best fit in figure 2.2. State the coordinates of both the points you use in your calculation. This must be selected from the line of the best fit. Give the gradient to the three significant figures and write the coordinates. Okay, let's go ahead to find out the coordinates at figure 2.2 of the graph. Here is the graph and we want to find out two coordinates for our graph. So I would select one here and one here, which is exactly on the line. And what are the coordinates of the first point is here. Yes, here is the x-axis and here is the y-axis, the 2 points. Okay, so if we find out, here is 0.0031. Now a square besides it should be 0.00312. That's how I find out. And so the x-axis value is 0.00312, and on y-axis if we find out here we end up, and so if it's 1.8 to 1.9, then I would say it is 1.875. This is how I would write it, 1.875. So this is log K1. So that's the first coordinate which we have done, and the second point coordinates are here. If we extend it to x-axis, let's see what is the x-axis point. You can easily draw it with the scale very faster, but as I don't have a scale here, okay, here we end up with this point. Okay, so here is 0.0033. This is 0.0033, 332, 334, 335, and this is 336. Okay, fine, 332, 334, 336, and okay, 337 it is. So it is 0.00337. I would write it is 0.00337. Okay, and on y-axis, let's see, it is here. I'll extend, so it's here. Fine, and yes, this is the point I'll expect. So this is 2.01 here, and this is 2.02. So 2.02 here, and this is how we get the coordinates for the 2 points. So here are the two coordinates which I've already noted down from the graph points which we had measured. Now if we want to find out the slope or the gradient, would say it's y2 upon y1 minus x2 upon x1. So here let's write 2.02 minus 1.88 upon 0.00337 minus 0.00312, and substituting all the values, I've got the value as 560. So it's 560 Kelvin is the gradient here. Okay, use the gradient calculated E1, E3 and equation 2 to calculate a value for the enthalpy change of the reaction delta H. Now we have already know that on y-axis it was log K1, on x-axis it was 1 upon T, and here is the constant. If we find out y is equal to mc, y is equal to mx plus c, so here is the constant which we can ignore, and if we substitute the slope, rearrange the equation here, then the slope has to be, the gradient has to be log k1 upon 1 by t, and if we rearrange this, we get minus delta h upon 2.303 into r, and that's how we get. Now if we want to calculate the value of delta h is this, so we can write gradient into 2.303 into r is equal to minus delta h. So we'll transfer this negative value or negative sign on the other side later on. So if we substitute all the values, it is 560 into 2.303 into 8.31, that's the value of r. And also remember, the value of r is in joules per Kelvin per mole, but we want our answer in kilojoules, so again we'll have to divide it by 1000. So let's substitute the value and find out. And so our value is 10.72 kilojoules per mole. So this is how we calculated. I hope calculation of gradient and rearranging the equation to use the gradient and find out the delta H value is very clear. You can have a look again. We rearrange the equation to get the gradient on one side, because gradient was the value which we had taken on y-axis, that is log k1, and the x-axis value, that is 1 by t, 1 by temperature, that is taken on one side, and the other values are kept on the other side. And then we rearrange again to find out the value of delta H, and so we had taken 2.303 into r on the other side to take negative value, and of course we have to add the negative sign here, that is minus 10.72 kilojoules per mole, and this is how we have got the value. And here our question 2 also ends.